Yeah. So, good evening, everyone. On behalf of the entire core team, India, it is my privilege to welcome you all today once again to our core program webinar series. So, our core program is a 4 years program project work that is being funded by NIH, National Institute of Health and Care Research, and in India, it is a including the four countries that is India, Colombia, Brazil, and Kenya. And in India, along with Jamia Millia Islamia, there we have collaborate with the Public Health Foundation of India under Professor Manu Mathur sir. And over the past few years, we had the privilege of conducting a series of webinars that are aimed to strengthening the research capacity and promoting excellence in oral health research. So we sincerely thank each one of you for your continued participation and encouragement, which has made this webinar series a meaningful learning platform. And today's session is titled Choosing the Right Sample in Health Research, a topic that was selected based on the suggestion and feedback received from many of our webinar participants. So we truly appreciate your valuable inputs, and we hope that today's discussion will help you all to gain greater clarity and confidence in selecting the most appropriate sampling strategies for your research. So before begin, I would like to request everyone to kindly follow a few webinar etiquettes for the assurance of our session. So firstly, please keep your microphone muted throughout the presentations and also try to avoid scribbling or annotating on the shared screen during the session time. We have reserved the last 15 minutes of for an interactive question and answer session. So during that session, you can turn on your microphone and video camera to ask the question directly, or otherwise type your question in the chat box and I'll be happy to convey them to the speaker of the day. Once again, thank you for all your cooperation. Now, with this, I would like to invite Professor Abhishek Mehta, who is leading the core program in India, to kindly come forward and welcome our distinguished speaker of the day and introduce him to the audience. Over to you, sir. Thank you.
Thank you, Varsha. Can you hear me?
Yes, yeah, you can.
Yeah.
You're
Okay.
audible.
Thank you and good evening, everyone. Thank you for joining to this webinar session today. It's my privilege to introduce Dr. Viswa Chaitanya Chandu. He is a faculty in Department of Public Health Dentistry at Government Dental College, Vijayawada, Andhra Pradesh. And Dr. Chandu has expertise in epidemiology, research methodology, biostatistics, and has been conducting various lectures, workshops on these topics. And he's also associated with many national and international journals as reviewer, as editor. So I can say he's one of the upcoming public health dentists in our fraternity. Uh, and the topic for today, I personally contacted him and asked him to uh, take this topic because there were many, as Barsha told, there were many questions on that in previous webinars also, and there were many requests for that. So with these words, I'll just hand over the mic to Dr. Vishwa and hope he has a good session. All of you are able to clear all your doubts with him. Over to you, Dr. Vishwa.
Yeah, thank you so much, sir. Thank you very much for the kind words. And I hope I'm audible.
Yes, you're on.
Yes, I'll start sharing my screen. And I think my video is visible as well. The slides are visible, right?
Yeah.
Yeah.
The slides are visible.
Yeah. Thank you very much. Very good evening, everyone. It is actually a privilege to be here with all of you this evening. And first of all, I'd like to thank the Public Health Foundation of India, the core program, and Jamia Millia University for having me here with you for this webinar. So coming to the topic, sample size and sampling techniques, it always is very interesting, not because of the topic itself, but because the expectations that are usually associated with the topic. Now, usually here there is a webinar, there is a presentation on sampling, sample size calculation. We intuitively expect that there will be a demonstration of a software. So the speaker shows where to enter your alpha, where to enter your beta, how to enter your effect size, how to calculate it, and click this button, you'll get your sample size. So we are not doing that here today. So instead, what we are doing is, as the title says, choosing the right sample in health research, and as the subtitle goes, why and who you study matters as much as how many. So let us keep the concentration a little less on the calculation of the number itself, and let us focus more on what happens before we get to calculate that number. So I think that is the right way of actually getting an insight into how accurately to calculate sample sizes. So these are the contents. As you can see, I have prepared them in such a manner that there are different stories, but they are built in such a way that each story leads into a different story. So as you can see, first we will see why samples are needed at all, why we do not work with populations, why we are working with samples. And then we will enter the ambit of hypothesis testing. So there comes the concepts of errors and power. And then we will see the decision trees of statistical analysis, which is very much essential for you to calculate your sample size. And then we will briefly discuss various sampling techniques that are there. And then the sample size calculation chain. I'll give you a brief demonstration of the G-star Power Toolkit. And then we will see some worked examples if time permits. And then let us try and consolidate what we have learned out of this webinar. So with that very brief introduction, so let me have this question first. So what research is about? Now, before we talk anything about alpha, beta, the entire machinery surrounding the null hypothesis significance testing, let us first consolidate what research is about. Now, I'll put it this way. So someone makes a claim and the entire discipline exists to figure out whether that claim is worth or deserving to be believed or not. But how do we decide that? So that is what research is all about. So first we have to understand, is that claim, is that statement precisely stated enough to be tested? So that is about your variables, that is about your hypothesis. And then the second question is, how can we fairly assemble evidence? So now we are entering into the ambit of sampling and sample size estimation. And how do we make sure we are not fooling ourselves? So there you are talking about your bias, your confounding and all. And how confident we can be about this not being a chance occurrence. So now we are talking about alpha, you are talking about beta, the 95% confidence intervals, your p-values. And then has this claim been tested well enough elsewhere too? Now you are talking about consistency and coherence. You are entering into the domain of evidence-based dentistry and evidence-based medicine. So this is the entire skeleton around which the quantitative research is built. So I'm being very explicit in stating that it is quantitative research. So we are not entering into the qualitative domain. In quantitative research, first we are asking about a hypothesis. So we are talking about variables, we are talking about data itself. And then how can we fairly assemble evidence? How do we make sure we are not fooling ourselves? Bias and confounding, where you discuss about the restriction, you discuss about matching, you discuss about randomization, you discuss about multivariate modeling, drawing all those directed acyclic graphs, all those things. So today we are actually focused more on the second and the fourth question. How can we fairly assemble evidence and how confident we can be about this not being a chance occurrence? So with that consolidation, so now we have arrived at a consensus that we are testing a claim. So no matter whether it is descriptive claim, an associative claim, or a causal claim, we are testing a claim. But what do we need to test it in the first place? So first, a claim needs to be worded precisely enough that it becomes something we can actually put to test, not just a general impression. So that is your hypothesis statement. It is in fact not a single hypothesis statement, it is two statements. To test a single claim, we need a pair of statements that between them cover every possibility, which are called the null hypothesis and the alternative hypothesis. So every hypothesis test starts here, turning a claim into a null and alternative hypothesis, which actually can be tested empirically. So now this is now most textbooks do not explicitly say this. The concept is implicit. They very clearly talk on what exactly hypothesis tests are, but these words are not such easily said out loud. So a hypothesis test is in statistical procedure that allows us to use data from a sample to draw conclusions for an entire population. So I always say whenever I talk on hypothesis testing, I talk on NHST, I always say this is the single most take-home message from hypothesis testing. So you are working on samples and you want to draw conclusions about the populations. So a hypothesis test is a procedure that allows you to do so. And then in technical terms, a hypothesis test evaluates two mutually exclusive statements about the population. It is about the population and determines which statement the sample data supports. So your hypothesis, very importantly, we have to understand and realize this. Your hypothesis is never about samples. Your hypothesis is always about populations from which you have drawn those samples. So I'm just repeating it. In technical terms, a hypothesis test evaluates two mutually exclusive statements about the populations and determines which statement the sample data supports. Now let us see the difference between what happens in a sample and what happens in a population. So what is the difference? What you are observing in a sample is a fact. After all, it is empirically being tested by us, empirically being estimated by us. But what happens in a population is a generalization question. So you are observing the samples and then you want to make generalizations about the populations. So because we are doing that, there is uncertainty when we are talking in the context of populations, but there is no uncertainty whatsoever when you are observing or restricting yourselves to the samples. And hypothesis testing, is it needed in samples? As I have already told you, hypothesis testing is never about samples, it is populations, it is about populations. So hypothesis testing is not needed for samples because you know that there is a difference. Let me give a simple example. Let us say you have a mean DMFT of 3.1 in one sample and a mean DMFT of 3.09 in another sample. Now there is a difference of 0.01 and there is a difference. You do not need a statistical test, you do not need a hypothesis test to tell that there exists a difference between these two samples. No matter how trivial the difference is, it is only 0.01, but there is a difference. You do not need a statistical test for that. But when you want to generalize it to the population, when you want to generalize that there exists a difference between the two populations from which these two samples were drawn from, there you need a hypothesis test. So very likely that this difference of 0.01 cannot be true in a population. So that is the basic understanding about hypothesis testing. So the sample is giving us facts. Hypothesis testing is the bridge that lets us say something about the population. So I think we are all very clear on this. So just a graphical representation of the same thing. What we intend to learn about is always the population, but what we get to work with is only the sample. So when you are learning about the sample, there is no uncertainty whatsoever. Let us log this in. There is no uncertainty whatsoever when you are dealing with samples. Uncertainty arises when you want to apply or generalize those findings to the entire population. That is the domain of inferential statistics. So hypothesis testing exists only because we work with samples, never the whole population, but we want to generalize our sample findings to the whole population. All right. So now I have told you that there are two mutually exclusive statements. One is my null hypothesis, the other one is my alternative hypothesis. So this is usually the question, why we have to start believing the null to be true? So why do we have to start believing the null hypothesis and then either reject the null hypothesis or failing to reject the null hypothesis? Why can't we start believing the alternative hypothesis to be true? This is a common question for those who are not trying to understand research methodology at the very beginning. So I will present three viewpoints for why null hypothesis is always the default position. I'll present a logical viewpoint, a legal viewpoint, and a scientific viewpoint. So now first let us see the logical viewpoint. In science, actually it is very difficult to prove something to be true beyond doubt. So there is a simple crow analogy. What if you have to prove that all the crows are black in color? So there is a claim that crows are black in color. How can you prove that crows are black in color? If you are to prove this, you have to catch hold of all the crows in the universe and you have to show that they are all black in color, which is humanly impossible. But what it takes to disprove this? Can you prove it to be false? If you can catch hold of a white crow, it is as good as proving that all the crows are not black in color. So science works logically in a similar way. It is very, very difficult to prove something beyond doubt in science. We all know heart is situated in the thoracic cavity on the left side. But the moment we say this in a generalized way, there comes a patient with dextrocardia. So there is no absolute truth in science. So there is always a certain amount of doubt. So you cannot prove something beyond doubt in science. So the null hypothesis logic, the null hypothesis default states that falsification is easy. Proving something beyond doubt is difficult. So instead of trying to prove the alternative hypothesis, you start with your null hypothesis. If you can disprove your null hypothesis, if you can reject your null hypothesis, it is as good as proving your alternative hypothesis. So that is the logical viewpoint for why we start with null hypothesis. And then coming to the legal viewpoint, we all know that with the exception of very few cases, we all know the starting point, the baseline stance from where a trial starts is that it starts believing that there is no association between the person and the crime. It starts believing that the person is innocent until he is proven guilty. So it is starting from a point where it assumes that there is no association between this person and the crime. That is essentially your null hypothesis. So that is the legal viewpoint. And then the most important and sound thing is your scientific viewpoint. Now, please pay close attention here for those who are interested in knowing why we actually start with null hypothesis. From the scientific viewpoint, this is the entire backbone around which the architecture of probability theory is built. When I say there is something, it can be so many things. Just say there is a box. I am asked to see whether there is something in the box or not. When I say yes, there is something, there is a possibility of so many things. There can be a fruit, there can be an eraser, there can be a pen, there can be a pencil. But when I say nothing, it just means nothing. So nothing or the null is the only practically possible value around which you can build a probability theory. If you just say something, something can mean so many different things. You cannot keep on building probability theories around all those possibilities. That is not practically possible. So the only practically possible value, which is universally opposition. So that is the scientific rationale for why we start with null hypothesis as a default. So these are the three viewpoints. And then going back to how we want to know about populations, but how we work only with the samples. Since you are working with samples and trying to generalize those findings to the populations, there is a possibility of making two errors. So in some instances, we may falsely detect an effect which is not there in the population. And in some instances, we may fail to identify an existing effect in the populations in our samples. So when you fail to identify an existing effect in the population from the data you have collected from your samples, you are committing to a type 2 error, which is also called as a false negative error. And when you are identifying an association which is not there in the population, you are committing a false positive error, also called as a type 1 error. So this is usually discussed with a courtroom example, right? So there are two possibilities: the person is really innocent or the person is guilty. And there are two judgments which the judge can pass. The judge can either declare this person to be innocent or adjudge this person to be guilty. So there is no problem when an innocent person is declared innocent, when a guilty person is declared guilty. But the problem comes when an innocent person is declared guilty. So there is no association between the person and the crime in reality, but the judge is finding one. It is a false positive association. And on the second instance, there is an association between the person and the crime, but the judge is failing to identify that association, which is a false negative error. So these are the two kinds of errors. And just log this in mind, because you are working with samples and because you are trying to make generalizations about the whole population, these errors are unavoidable. So you have to adjust for these errors somehow, and we are doing that in our sample size calculation. So that is a rationale for why the errors are being presented. That is a rationale for why we are discussing hypothesis testing in the sample size class or a sample size webinar. So first, let us try and make sense of what exactly these errors are. So we have spoken about alpha error, we have spoken about beta error, which are the false positive and false negative errors respectively. So first, let us see what alpha is. Alpha defines how strong the evidence from a sample must be before we conclude that a difference exists in the population. So very straightforward. So it is like an evidentiary standard. It is like a pass mark, which we are already setting before we start the study. It is not something which is retrospectively done. And it signifies how strongly the sample evidence must contradict the null. And null is always about the population. I already told you that hypotheses are always about the population. So it signifies how strongly the sample evidence must contradict the null in order for us to reject it for the population parameters. This evidentiary standard is formally the probability of rejecting a true null hypothesis. Very simple. The probability of rejecting a true null hypothesis is what your alpha is. But the problem comes when you are interpreting in the way it is not supposed to be interpreted. Usually, when I read it for the first time, I thought by an alpha of 5%, I mean I am okay to commit an false positive error of 5% in my study in this particular instance. But it does not work that way. It is always about replication. It is always about the probability theory. So the real meaning of alpha is in a population where the null hypothesis is actually true. So that is a conditional statement. In a population where the null hypothesis is actually true, if I repeat this study endlessly, if I do the same thing again and again, I am allowing that, I am accepting that 5% of my results would be false positive in nature because I am working with samples. So even at the expense of repeating myself again and again, So I want to inculcate this idea into the brains that because I am repeating it again and again, and because I am starting with a null hypothesis as a default, so there is a probability of making mistake because you are working with samples. So this is the essential meaning of alpha. In a population where the null hypothesis is true, if you repeat the study again and again endlessly, I am accepting that 5% of my results would be false positive because I am working with samples. So is it mandatory to go with 5% alpha always? No, because some studies they demand 1%, some studies it is okay to relax it to 10%. So it is entirely contextual and circumstance driven. It is not a rigid value that you always have to keep. Actually, Ronald A. Fisher, the scientist who introduced the very idea of alpha, these are his exact words. No scientific worker has a fixed level of significance at which from year to year and in all circumstances he rejects hypothesis. He rather gives his mind to each particular case in the light of his evidence and his ideas. So alpha is something which is not supposed to be fixed. It is entirely contextual and it is circumstance driven. And in fact, I'll just go a little further to the p-values. Usually we reject the null hypothesis when p-value is less than or equal to 0.05. And why do we do that? We do that because we started our study accepting an alpha error of 5%. What if we started our study accepting an alpha error of 1%? We would reject null hypothesis only when the p is less than or equal to 0.01, not 0.05. So what your p-value is just making sure whether you are crossing the evidentiary standard you have set before you have started your study or not, right? But again, going back a little into the history, actually, Ronald A. Fisher never intended the p-values also to be a rigid cutoff. The actual idea is just p-value act as a sliding scale of evidence. The moment you come from 0.01 to 0.001, you have a strong evidence. The moment you come from 0.1 to 0.05, you have strong evidence. So that's what the interpretation of p-values are supposed to be. That's how alpha were never meant to be a rigid cutoff. But when this concept of alpha and p-value are integrated into the Neyman-Pearson framework afterwards, then we started believing p-value to be a rigid cutoff. So the entire concept of p-value less than or equal to 0.05 being a success and p-value greater than 0.05 to be a failure originated from there when we tried to integrate alpha and p-value into the Neyman-Pearson framework. All right. So now making sense of beta. So just like how alpha is conditional on the statement that if null hypothesis is true for this population, beta is conditional on the statement that if alternative hypothesis is true for this population, if there is a real effect in this population, if I repeat the study again and again, so many times, endlessly, I am accepting that I would commit a false negative error 20% of the times. So what does that mean? I am accepting that 20% of the times I will fail to identify an existing effect. So just like how in alpha, we are okay with accepting 5% false positive results, here we are accepting that we are okay with accepting 20% false negative results. And again, is it mandatory to go with 20% beta? No. Just like how 5% alpha is not a mandate, 20% beta is also not a mandate. So we are calculating in advance how much data is needed to keep the probability of each of these two errors down to a level we have explicitly chosen to accept. So these are some things which we are accepting before we start the study itself, before we start the sample size estimation itself. And what is power? Power is just the complement of beta. It is your ability to detect an effect which is existing. Just like how beta is your inability to identify an existing effect, the complement is your ability of identifying an existing effect. So since it is complement, if your beta is or your false negative error is 20%, your power is 80%. If your beta is 10, your power is 90, as simple as that. And now there comes an interesting question. Is one error worse than the other? So earlier I was talking about is 5% alpha mandatory, is 20% beta mandatory. And this is the critical value which informs you about the decision. So see what happens. There is a critical value. If I move that critical line towards the right, what I am making? I am making my type 1 error to be less, but that is at the expense of increasing my type 2 error. And what happens if I move the critical line towards the left? I am decreasing my type 2 error, but that is at an expense of increasing my type 1 error. So it is entirely circumstantial. Take the, let us say, take the example of a simple sensitivity test or a screening test, right? So in a screening test, what do you want to do? Even at the expense of giving some false alarms, even at the expense of identifying some people who do not have the condition to be having the condition, you do not want to miss any person who is actually having the condition. So in a screening test, even at the expense of making a little more alpha, you do not want to commit more and more beta. And now come to the diagnostic test. In a diagnostic test, what do you want to do? You do not want to identify a person who is not having the disease to be having a disease in a diagnostic test. So even at the expense of making a little more beta, you do not want to make a more alpha in a diagnostic test. So it is entirely circumstantial. That is a trade-off. When you are at a given sample size, I'm repeating, it is not with an increase in sample size. Usually it is misinterpreted for different sample sizes. But for a given sample size, alpha and beta are trade-offs. If you are increasing on your alpha, there is some disturbance. Yeah. If you are increasing on your alpha, then you are losing on your beta. I mean, if you're gaining on your beta. If you are increasing on your beta, then you are gaining on your alpha. And now this is, I will say these are the two most busiest and two most technically demanding slides. I want all of you to please pay close attention to this, because the intuition definitely helps in understanding hypothesis testing in a much better way. Yes. Now I have a null hypothesis curve and an alternative hypothesis curve. And this is very, very important for sample size estimation. Actually, in understanding how sample sizes are calculated that way, this is very, very important. So there is a null curve and there is an alternative curve. And what does the null hypothesis curve say? The null hypothesis curve say, if there is a population where there is no effect, if I repeat the study endlessly, what are the range of values I would keep getting? So as you can notice, what is the central point in the null hypothesis curve? The central point is 0. So I'll just, the central point is 0. And there is another curve, which is the alternative hypothesis curve, where the central point is 3. And what does alternative hypothesis curve tell you? If there is a real effect in the population, I am repeating, if there is a real effect in the population, and I repeat the study endlessly, what is the range of values I keep getting if there is a real effect in the population? And here, the central value is 3. And what is this dispersion? What is this spread around the central value? It is nothing but sampling variation. So in case of null hypothesis curve, the spread around 0 is your sampling variation. Similarly, in the case of alternative hypothesis, the spread around 3 is your sampling variation. Now I'll show you what are the central values of both these curves. In null hypothesis curve, obviously the central value is 0, because the null essentially states that there is no difference. And in the alternative hypothesis, in this particular example, the central value is 3, which means you are anticipating an effect size of 3 between the two populations from which these two samples came from. So here, let us keep it simple and discuss an independent sample t-test. So you have two samples drawn from two populations. So you are anticipating an effect size of 3, which means you are expecting a mean difference of 3 between the two populations from which these two samples came from. So now we have two curves, the null hypothesis curve and the alternative hypothesis curve, sitting side by side, and they share a common x-axis, which is the mean difference, because it is the independent samples t-test we are talking about. But we need some more. What we actually seek to have is we need a critical value, and that critical value should enable me to make a decision whether to favor alternative hypothesis or null hypothesis. And what exactly is the critical value? And that critical value, it tells you, to the left of that critical value, you fail to reject the null hypothesis. To the right of that critical value, you reject the null hypothesis, right? But this is something very, very important. This critical value is not something you can move wherever you want it to be moved. This critical value is nothing but your alpha, and this critical value is only a property of the null hypothesis curve. I am re-emphasizing on this. This critical value, or the line which I have drawn in red, has nothing to do with your alternative hypothesis curve. It is a property of the null hypothesis curve, and it is determined exclusively by your alpha. So what this critical value actually is that only 5% of the area under the null hypothesis curve will be to the right of this critical value. If you notice, so this is the area which is to the right of this critical value in your null hypothesis curve. That is what you call as your alpha region. So it is fixed. You cannot adjust it. You can adjust it only at the time of sample size calculation, only when you are deciding what your alpha is meant to be. Once you have decided that your alpha is 5%, this critical value is fixed on your null hypothesis curve. It is something beyond which only 5% of the area of your null hypothesis curve lies. And this is alpha region. In this region, the results are so extreme that when null hypothesis is true, these results cannot be due to sampling variation. So when your test statistic lies to the right of this critical value, what you say is that you reject the null hypothesis. And what happens on the opposite side? So now this is the region which is to the right of 0, which is to the right of the null effect. And this is the region where there can be some effect, but you are failing to reject the null hypothesis because this is to the left of the critical value, and this critical value is the rigid cutoff you have accepted before the start of your study itself. So now if you understand this alpha region and the beta region, then the sample size estimation becomes a lot easier. Now I'll show you how it is directly linked to your sample size. Now I have drawn only the null hypothesis curve. I have not placed the alternative hypothesis curve yet, but I do have my critical line. As I have already told you, this critical line is only a property of the null hypothesis curve. And beyond this critical line, there is only 5% of the area under the null hypothesis curve. So this is a fixed value. Now I am also fitting the alternative hypothesis curve. So now there is an overlap between the null hypothesis curve and the alternative hypothesis curve. Now what happens if I increase my sample size from n is equal to 60 to n is equal to 300? So this is my null hypothesis curve now, and this is my critical value now. So now what happened to the critical value? It actually shifted towards the left relative to the previous example where n is equal to 60. The reason is the null hypothesis itself, the null hypothesis curve itself has shrinked. It was broader earlier. Since the null hypothesis curve has shrinked, since this line is only supposed to cover 5% of area to the right of this null hypothesis curve, this also has shifted a little towards the left. And now see what happened to my alternative hypothesis curve when I increase the sample size. My alternative hypothesis curve also shrinked. But what happened to my central values? My central values never change. Because the central values are with regard to the population which are true. You are anticipating that the difference between these two populations from which these two samples came from is 3. So that would never change. What can change is with increase in your sample size, your standard error is decreasing. Your precision is increasing. So that is the reason why the spread of the curve is now shrinked. I hope you understand what I'm trying to say. So with increase in sample size, what is happening to my alpha? My alpha is actually coming a little towards the left because it is a property of the null hypothesis curve which is getting shrinked. And what is happening to my beta? My beta is also decreased because now the overlap between the null hypothesis curve and alternative hypothesis curve is not as much as it was before. And what you are essentially gaining is the power of your study. So because you are decreasing your beta region, since power is a complement of your beta is increasing. I mean, power is increasing. So that is what we are doing in sample size calculation. So I hope it is clear for everyone. So I just want you to remember that this critical line is a property of the null hypothesis curve only. It only covers, I mean, beyond this critical line, 5% of the null hypothesis area would be there. Null hypothesis curves area would be there. And this critical line, since it is only a property of the null hypothesis curve, it only happens to traverse the alternative hypothesis curve also, because there is some amount of overlap between the null hypothesis curve and the alternative hypothesis curve. When you increase your sample size to infinity, this overlap between the null hypothesis curve and alternative hypothesis curve would go. So that is where you are moving close to census. That is where you are moving from samples to populations. So that is the idea of hypothesis testing. And this is one more interesting thing. So when I say 5% is a property, the alpha is a property of the null hypothesis curve in a two-tailed test. Now I am talking about a two-tailed test. So 2.5% of the alpha is to the left tail of the curve and 2.5% of alpha is to the right tail of the curve. And this is something which we call as a Z table, the standard normal deviate table. And as you can see, the standard normal table gives the area to the left. Now let us go back and see this line. So this line in a two-tailed test is covering only 2.5% of the area under the null hypothesis curve to the right of it. And there will be another line here which we have not drawn. And what is the area under the curve which is to the left of this line? So barring the 2.5%, we have 97.5%, otherwise also called as 0.975 of the area under the curve to the left of that line. And that is what the standard normal deviate table gives you. So where is 0.975? 0.975 is here. And what is the Z value associated with this area under the curve? it is 1.9, and the second decimal is 0.06, so it is 1.96. So when you calculate the sample sizes as Z alpha square PQ by D square, the reason why you substitute Z alpha with 1.96 is this. Because the area under the curve, which is to the left of this particular line which you have drawn at a given alpha of 5% in a two-tailed test, is 1.96. So Z alpha for a two-tailed test at 5% alpha is 1.96. And what if it is a one-tailed test? So the entire rejection region is on one side. So now I am looking at the area under the curve, which is to the left of it is only 0.95. 0.9505 is the closest value here. So if you see the corresponding Z, it is 1.6 and the second decimal is 0.05. So 1.64 or 1.65 is the Z alpha in case of a one-tailed test at an alpha level of 5%. So I hope you understood why we substitute 1.96 and 1.64 for the two-tailed and one-tailed test respectively. All right. So that is about hypothesis testing and all the technical intricacies of hypothesis testing. And now let us see the data types. This is very important because ultimately when you are doing your sample size estimation, it depends on what statistical test you are doing, right? How you want to analyze your data. But for that, first we need to understand what kind of a data it is. So this is a broader classification. I'm sure we do not have to extensively discuss on this. Qualitative data, nominal, and you also have ordinal.
Meeting. Bye.
Which is ordered or ranked. So the classic example can be your socioeconomic status, lower, middle, upper, and upper. And then you have the quantitative data, discrete, countable whole numbers, and continuous, any value in that range. And this is another classification. Interval and ratio comes from a different classification compared to the classification basis for discrete and continuous. When you are classifying your data as discrete and continuous, your emphasis is on whether it is a whole number or it can be any value in a range. But when you are classifying the data into interval data or ratio data, your question is whether true zero exists or not. So I can probably give you a dental. Usually they give temperature in Celsius and temperature in Kelvin as an example for interval and ratio. Let us try and think of something which is more dental. I think your salivary pH is a very good example. See, in salivary pH, the moment you say, let us say there are two salivary pHs. Salivary pH is 4, salivary pH is 6, or let us say it is 8. So these two salivary pH are not divisible. So when I say the salivary pH is 8 and salivary pH is 4, the person who is having a salivary pH of 8 is not having 2 times more salivary pH than the person who is having a salivary pH of 4. It is not a ratio because the actual hydrogen ion concentration is something which is 10,000 times more, right? So ratio does not make sense there because pH of 0 does not make sense at all. Right, so that is an appropriate example, I think. And ratio, there is a true zero. Your DMFT score can be a good example. There is a true zero. When you say DMFT is 0, there is a true zero. And DMFT of 2 and 4. DMFT of 4 is exactly twice the DMFT of 2. So that is the ratio interpretation. But what I want you to understand is that when you are choosing a statistical test, this distinction between interval and ratio does not really matter because the statistical test remains the same. But what differs is that the way how you interpret it. Now, in the earlier example, when you see salivary pH of 4 and 8, you cannot say group B had 50% more salivary pH or 100% more salivary pH than group B. That cannot be the interpretation. So easily we can be forced to draw that interpretation, but since the data is not clear ratio, you can only say there is a mean difference of 4. You cannot talk in terms of ratios. So that is one care we should actually take. So that is about the brief data types. And this is choosing the right statistical test. So I have developed it with Claude Sonnet 5. So what are you comparing? If you are comparing categorical variables, so the first question is whether this is independent data or paired data. If it is independent data, the next question is, what about the expected cell count in all cells? If it is less than 5 in any of the cells, then you have to go for a Fisher's exact test. If it is greater than or equal to 5, you can go with a chi-square test. And how many related, if it is paired data, how many related samples are there? If there are 2 samples and it is only a dichotomous data, then you can go for a McNemar's test. If there is 3 categories, 3 levels in the variable, and there are 2 samples, you can go for a Stewart-Maxwell test or a test of marginal homogeneity. And if there are 3 paired groups, but there is binary data, then you have to go for a Cochrane skew test. So it is in SPSS, it is under the non-parametric test where you compare proportions. And then if it is a numerical data, the first question, is it independent or paired? If it is independent and there is only one sample involved. So when one sample is involved, it obviously is independent. And you are talking about parametric tests where the data is normally distributed, you are going for a one sample t-test. If it is non-parametric where data is not normally distributed, you are going for a one sample Wilcoxon. And now there are 2 groups. Those 2 groups are independent. Parametric distribution, normal distribution, you are going for unpaired T, the non-parametric alternative for which is Mann-Whitney U. And paired, you are going for a paired t-test. Wilcoxon sign rank test is your non-parametric alternative. There are 3+ groups. Actually, it should be 2+, not essentially 3+, because you can apply one-way ANOVA even if there are 2 groups. It essentially gives the same result as your independent samples T. So 3+ more groups, independent in nature, you go for one-way ANOVA based on the distribution. If not normally distributed, you go for a Kruskal Wallis ANOVA. If there are repeated measures, 3 or more occasions, baseline 3 months, 6 months, and 9 months, you go for a repeated measures ANOVA based on the distribution, and you go for a Friedman's test if it is not normally distributed. And now, how about the relationships between the variables? Because we have to calculate sample sizes for all these occasions, right? Depending on the statistical test given at a given alpha, at a given power, at a given effect size, you have to calculate sample size on all these instances. So coming to the relation between variables, is it just association you are talking about? Is it just correlation or association you are trying to draw? Or do you want to actually make predictions? If you just want to correlate or associate, then depending on the distribution, if it is normal, then you can go for a Pearson distribution. If it is non-linear, if it is not normally distributed, you can go for a Spearman's rank correlation. And though it is not within the context of this webinar, I just want to give you a quick tip that whenever you are plotting correlation, before you choose your test based on your normality assumption tests alone, be it Kolmogorov, Smirnov, or be it an omnibus test, what I want you to do is please plot your data without looking at your scatter plot. Never decide your test based on the normality distribution assumption statistics alone. And then coming to the type of outcome variable where you are wanting to make a prediction, if it is a continuous variable, you are going for a linear regression. It is a simple linear regression or multiple linear regression, depending on how many independent variables are involved. If it is binary or categorical, you can go for a logistic regression. If it is binary, we call it binomial logistic regression. If it is multiple categories involved, you call it as a multiple logistic regression. And then if it is a count data, so usually this is a problem in the conventional dental examples where DMFT scores are treated as continuous variables where essentially they are count data. So if it is a count data, you go for a Poisson regression. If that count data is over dispersed, you have to go for a negative binomial regression. And if there are more zeros, which is usually the case with large population DMFT studies, there are so many zeros. In that case, you have to actually go for a zero inflated negative binomial regression. And then you have the reliability and measurement agreement statistics as well. So what I want you to understand is we have understood alpha, we have understood beta, and now we are deciding which statistical test to choose given a scenario. And now let us come to sample size estimation. So before we come to sample size estimation itself, let me ask you a quick question. Why do we need to sample at all? Why can't we study populations? So I'll give you a quick moment to actually type in the chat box that why not just study everyone, why we are working with samples. Just quick 30 seconds. If anyone can please type in the chat box that why we are sampling, why we are not studying whole populations. Time consuming, sometimes impossible. Thank you. Sample is a representative of the target population. Resources are limited. Vikrant Monti sir, thank you. Resources are limited. All right, I don't want to cut down on my discussion time, so I'm closing the chat box. So usually, as you can see, most of the responses are around the practical possibility. It is about logistics. It is about feasibility. But the real answer is a little broader than that. So the reason why we sample is that there are 5 problems. One, the definitional problem of everyone. When I say early childhood caries, children with early childhood caries, am I talking about those children who are having early childhood caries in this moment? Or is this also about those children who had early childhood caries in the past? Or is it also about those children who will have early childhood caries in the future? So this concept of everyone, this concept of whole population is always theoretical in nature. It is not a censusable list. So no matter how hard you try, you cannot reach everyone. And the second problem is a consequential inferential problem. So now let us say somehow you manage to catch hold of every person who is having that condition, a given condition. Now, who are these results for? Are these results only for those people whom you have studied? Or are these people also for those people who had this condition before? Or are these results also for people who are going to develop this condition? Who are these results for? Science rarely asks the question about these specific people whom you study. Science rather asks a generalized question, and everyone can never be reached. So that is another problem. And then the ethical problem. So as you are saying, wastage of resources is an important ethical concern. When you can find something with these many resources, why waste these many resources? I'll give you a simple example. I'm asked to study the prevalence of fluorosis in a given region. I calculated my sample size based on the prior established literature, taking a baseline prevalence. I got my sample size to be 1,200. Now, what if I study 20,000 children instead? Am I going to gain on precision? Definitely yes. But would I be wasting so many resources, wasting so much time, wasting so much material, wasting so much money, so many dentists, pulling so many children out of the class for examination, getting permissions from all those school teachers, getting all those parental consents? For that negligible increase in precision, am I actually willing to make all these sacrifices? So your sample size calculation also need to be ethically defensible. So that is one more thing. And then of course the commonly agreed practical problem, the logistical problem, and then the counterfactual problem. So I will reserve talking about counterfactual problem towards the end. If we have time, we will discuss about the counterfactual problem, or someone can actually ask this in the question. Then we can discuss the counterfactual problem. So what we are doing is we study a sample instead, a smaller manageable group, and use it to speak carefully and with a known margin of uncertainty about the population it came from. A very, very beautifully crafted statement. And then coming to the sampling techniques, you have the probability sampling techniques and the non-probability sampling techniques. In your probability sampling technique, always you have a known non-zero selection probability. So every participant has a known chance and every participant has a non-zero chance. In case of simple random sampling, every participant also has an equal chance because everyone can be selected at a similar probability rate. So I don't have to discuss about what simple random sampling is. You have a sampling frame and you have actually a list of everyone where you can randomly pick participants depending on how much your sample size is. And then systematic random sampling, it is the every kth unit. So it is also very good in terms of representativeness, in terms of not having selection bias, particularly if the sampling frame is not defective. So if the sampling frame is defective where you can see a pattern, then systematic random sampling can be detrimental for representativeness. And also stratified random sampling. So usually simple random sampling is considered the ideal probability sampling technique. But I have a different opinion when I read a lot of data, especially in dental public health, especially in our context. Stratified random sampling is in fact the better sampling technique. The reason why I say this is what you are doing is you are eliminating so many confounding factors at the design stage itself. What if you have a sampling frame where everyone is treated equal? But you know that there is an important difference between rural population and urban population. You know that there is an important difference based on socioeconomic status. So what stratified random sampling is doing is it is actually dividing the people, the population into strata, and within each strata, you are again doing random sampling. So representativeness is not lost, and even the characteristics which you want to retain in the sample, they are also not lost. So stratified random sampling, if done in a efficient way, it is very good. And then cluster random sampling where you actually select groups and within that group you get to examine or get to interact with everyone. And then the multi-stage random sampling, multi-stage cluster random sampling, which is one of the most practical things to do when you are going for something like a national survey, national oral health survey, national mental health survey. We all do this using the multi-stage cluster random sampling. So once you start with states, then you go to the districts, then you go to the revenue divisions, then you go to the villages, then you go to the families, the households, and then finally you go to the participants. So again, at every stage you are doing random sampling. You are not selecting all the people within the cluster, like cluster random sampling. Because the meaning of cluster, see, this is one area where usually people get confused. When I say everyone is recruited in cluster random sampling, and when I say in multi-stage cluster random sampling, every person in the cluster is not selected, I mean clusters in a different way. So in cluster random sampling, cluster is my unit of sampling. Whereas in multi-stage sampling, by cluster, what I mean is those people who are just sharing a similar set of characteristics from whom I am randomly selecting a few. So the context in which the expression cluster is used is different between these two things. Now coming to the non-probability sampling techniques, you have the convenience sampling where whoever is easiest to reach, you reach those. You have purposive sampling where you are looking for a deliberate trait, so which is very, very important actually in qualitative studies. And then you have quota sampling where you have fixed number per category, and then those fixed numbers are conveniently picked. If those fixed numbers are not conveniently picked but randomly picked, it is nothing but stratified random sampling. Since once you made the quota, you are conveniently picking them using convenience sampling. We call it as quota sampling, and we are listing it under the non-probability sampling techniques. Otherwise, this is nothing but stratified random sampling if it is randomly done. And then the snowball sampling, where sometimes there will be scenarios where you're dealing with drug peddlers, you're dealing with sex workers. So it is very important to go from one person taking the lead and going to the another person. So it is a very a pragmatic approach, snowball sampling, when you're dealing in such scenarios. So these are various sampling techniques. And these are the important sampling considerations in selection probability. The selection probability in probability sampling is known and non-zero. In selection, the selection probability in non-probability sampling is unknown. Of course, it is not known because you are depending on either a deliberate trait, identifying a deliberate trait, or you are depending on what is easier for you to do. And then the choice nobody generally questions, but definitely worth knowing in non-probability sampling technique is that just go back to your alpha definition. Just go back to your p-value definition. What do they say? My p-value says if the null hypothesis is true, if the null hypothesis is true, that is the inference of the p-value. If it is true, what is the probability of me getting a difference, an effect, which is at least as extreme as that I found in my sample just because of random sampling variation? Now look what is peculiar about this statement. This statement is conditional on the fact that the null hypothesis is true. But in non-probability sampling technique, you are not replicating the study using randomly picked samples at all. These are not randomly picked at all. So the concept of alpha, the concept of beta, the concept of 95% CIs, the concept of p-values does not exist for non-probability sampling techniques. So though you can calculate your standard error because it is just standard deviation divided by the square root of n, they are technically meaningless. So just have that in mind. And then not all sampling techniques cost the same. Very, very important. Because when people start sharing common set of characteristics, when people are very similar to one another, what happens is they are not independent anymore. For example, in simple random sampling, I'm taking 20 people. Each person is giving me independent information. Whereas I'm doing the same in cluster random sampling, what is happening? The amount of information which person 2 will be giving me is already explained to me in some manner by person 1 by virtue of them belonging to the same cluster. So it is just like, what do I say? It is just like taking a photocopy 20 times. You definitely have 20 papers. You definitely have 20 times more information, but it is not 20 times more knowledge, right? So that is the problem with cluster sampling. That is the problem with multi-stage sampling. And that you address using the design effect. So because all these sampling techniques, they assume that you are simple randomly selecting the sample size. So once you get a sample size, but your sampling technique says it is not random, it is not at least simple random, it is not simple random, then you have to increase your sample size, multiply your sample size with something called as a design effect, which is calculated by 1 plus b minus 1 into rho, where b is the number of units per cluster. So how many units or how many participants are there per cluster, and rho is the correlation between these things. It can be the ICC, the intra-class correlation coefficient between people within the cluster. So coming to the software, there are so many softwares. G-star Power is there. PASS, which is more technically useful in lot of AI multi-rater, multi-agreement studies. We are using PASS nowadays. Enquiry, SAS, EpiInfo, Stata, R, OpenEpi, so many things are there. But I feel G-star Power is one of the most intuitive, easily used softwares. And the sample size chain, it goes this way. So you have a research question, you framed a hypothesis, you listed what your outcome variables are, you identified your study design, you chose what your statistical analysis is, you identified your effect size, then only you can calculate your sample size, and then only G star power comes into the picture. So when I said it is not a demonstration of the sample size estimation software at the beginning of this webinar, I meant this. So there is a whole lot of decisions you are getting to make before you actually get to use the software. So that is very, very important to identify when you are calculating the sample size. All right. So now let us go to G star power. Okay. So in G star power as a tool, actually by power analysis, we are meaning 5 things. So these 5 options are there in G star power as well. I'll just show you in a practical demonstration. I think we have 5 minutes left. So a priori, you have a given alpha, which you have chosen before you started your study. You have a chosen power, which is a complement of beta. There is no reason why G star power list it as power. They can instead list it as beta also, because it is a given beta which decides what your power is. And then you have a given effect size. Then you are trying to calculate your sample size. So this is one way. So just think of it like a simple linear equation where there are 4 variables, right? A multiple linear equation where there are 4 variables. When you know 3 variables, you will obviously get to know the 4th variable. You can just simply calculate it based on the formula. So in the a priori method, we have power, we have alpha, we have effect size, and we are calculating the sample size. There are so many other types of power analysis where you have the sample size a priori, you have the effect size, you have the alpha, and then you calculated the power post hoc. And there can be instances where you calculate the alpha and beta instead, given a ratio of alpha and beta, given an effect size, and given a sample size. So these are all the possibilities, but in this class, we are seeing only the sample size derivation using power, alpha, and effect size. So I'm skipping this. Yeah. So coming to the effect size, enter what you actually know. So G star power's determine button you have to use. So do not depend on what Cohen has suggested as which are the default effect sizes. I actually have a list of all these effect sizes. So for t-test, what is a small effect size, what is a medium, what is a large, but these are the defaults. When you don't have a data in hand, when you don't have previous literature, when you cannot afford to do a pilot study, when you cannot do a sensitivity analysis, then you have to depend on these defaults. Otherwise, please do not depend on the default effect sizes by Cohen. So this is the actual article by Cohen, the power primer. Yeah, very beautiful article to read. And in fact, he has actually given some examples where to detect a medium difference between 2 independent sample means, that is an effect size of 0.5 at an alpha of 5%, we actually require n is equal to 64 in each group. If you do the same thing in G star power, you will essentially get 128 participants with 64 in each group. So these are just worked examples around predetermined default effect sizes, but as far as possible, try not to depend on these default effect sizes. Now we will see a couple of examples and then consolidate. So here the question is, do children using fluoridated toothpaste have lower mean DMFT than those who do not? So the study design is cross-sectional study, and I am willing to use 2 samples or independent samples t-test. My outcome variable is DMFT index, which is a quantitative variable. I'm just switching to the G star power software. I hope it is visible. So tests, I'm going to select means to independent groups. So I'm going to select, so this is what I'm talking about, type of power analysis. By default, we will have the a priori sample size analysis, but you can always change it to compromise criterion, post hoc sensitivity, depending on your context. So now what do I have to enter? So I'll say this is a 2-tail test. These are my default effect sizes. 0.2 is my small effect size, 0.5 is large, and 0.8 is 5 is medium, and 0.8 is large. But we will always try to determine the effect size. So based on the previous literature, what is the mean in group 1, what is the mean in group 2, what is the standard deviation in both these groups, and then you just calculate what the effect size is. So in this context, my effect size is 2. I just extrapolated this to this. And when I calculate, it is only 8 per each group. So that is how you calculate your samples. And using the software actually is very easy. And in fact, I'd like to draw your attention to this particular graph. So this curve in red is your null hypothesis curve, where which I have shown you when I am trying to give you the intuition of why hypothesis test is important and how you understand the critical line. And this is your alternative hypothesis curve. So notice what happened. Your critical line is here. This is your alpha region, which I showed you previously, and this is your beta region. Now I'll do one thing. Just remember the amount of overlap here. And now I'll do one thing. I'll actually make the effect size to be 5. Or I'll do one thing. I'll actually make the effect size to be 0.02. So what happened to my sample size? My sample size increased, and look at the overlap. The overlap now decreased. So that's what I tried to show you in the earlier intuitive graphical demonstration. And then you have paired design. You can select tests. You have to compare the means, two dependent groups, matched pairs. It asks for effect size, it asks for alpha error probability and your power. And I'll just show you repeated measures and then we will close this demonstration. So in repeated measures, it actually asks what is the correlation among repeated measures, which is very important. Because in repeated measures, it is the same person who is being evaluated on a different occasion. So the values are more likely to be correlated with the previous examination that you have to feed the software. If this correlation is more, then the sample size the software gives you is less. If this correlation is less, then the sample size of the software gives you is more. So we just have to keep this in mind. And when you do not have an idea of what exactly to choose as your correlation, 0.5 is usually the default. So yeah, I think we will stop it there. And in G-star power, there is no clustering built in. So once you know that there can be clustering depending on the sampling technique that you chose, you calculate the sample size and then you multiply it with a design effect. So yes, consolidating good sample size estimation is not about numbers. It is about making the right methodological decisions before the calculation even begins. So that's why G-star power is actually at the rightmost extreme of the entire sample size calculation chain. So with that, I think it's time to conclude my part of the session. I'm happy to take the questions. And I'd like to take this opportunity to thank Public Health Foundation of India, the core program, Jamia Millia University, Abhishek sir, Dr. Barsha for coordinating everything and giving me this opportunity. It is really a privilege interacting with all of you this evening. Thank you.
And thank you so much, sir. It was really an insightful session. But we have one question in our chat box, if you can see, sir.
Yes. Our hospital-based studies have a convenient sampling technique. Do we apply convenient sampling technique when we don't have a fixed denominator? Yes. Now, this is an important practical question. So I'd like to take a context and explain this. Now, let us say I am validating a questionnaire, right? When I'm validating a questionnaire, the first step is I have to generate an item pool. When I'm generating an item pool, do I actually have to go for a probability sampling technique? Probably no. I can depend on convenience sampling technique there because I'm just inviting ideas. But when I actually want to use that validated questionnaire to measure the prevalence of that property, to measure the mean value of that property, because there I am generalizing my findings to the entire population. Their convenience sample cannot work. So it entirely depends on the context. And there will be occasions where convenience sampling is the only possible thing for you. So please do not understand that non-probability sampling techniques are bad. There is nothing which is bad and there is nothing which is good. It entirely is circumstantial. So whenever possible, depending on what your research question is, you choose either probability sampling or non-probability sampling. And how do we effect for class stratification in a sample size estimation? So when you are actually stratifying, when you are doing stratified random sampling, you do not actually have to adjust. That's what I was trying to say when I said stratified sampling technique is, in fact, it could be better in some instances than the simple random sampling technique. But when you are doing for a cluster random sampling, yes, you have to adjust. And sometimes, especially in the case of multi-stage cluster random sampling, there is no fixed number of participants for a cluster. In case of a cluster random sampling, you have fixed number of participants per cluster, and there you can use 1 plus beta minus 1 into rho, where beta is the number of participants who are there in the cluster. In multi-stage cluster random sampling, there are so many stages, there are so many clusters where you cannot possibly apply this. So the default is that you generally choose something which is 1.5 to 2. That is the default. I'm not saying you have to use 1.5 and 2 all the time, but when you do not have no substantial evidence to back your decision, 2 is usually the default.
Yeah, Dr. Vishwa, just before we conclude, like I want to ask, like you are saying, like convenience sampling, like you don't need a particular number, but yeah, but still you will need some number. Like people will
Yes, sir.
ask, like the
Yes.
either uh, just to extend my point that maybe we can have a time frame in which the how many people we got for
Yes.
our sample, like or what it is? If you can
Yeah.
just explain
Sir,
it.
yeah. Earlier, when I answered that question, the question was not relating to size. They have asked, our hospital-based studies have a convenience-based sampling technique. So there we were just commenting on the sampling technique. We were not commenting on the sample size. Sample size is something which you definitely need before you think of the sampling technique. Because only when you know that this is the sample size I am going to recruit into my study, then you can go ahead and sample. But that information of what sampling technique you are going to use in your recruitment is indicative of what design effect you have to use in your sample size estimation. So definitely, even for convenient sampling technique, you need a sample size, but whether you are using simple random technique to arrive at that sample size, or whether you are depending on convenient sampling to arrive at that sample size, that is a different question.
Okay.
And sir, there is one more question from Dr. Kirti. What is the procedure to select PPS sample, probability proportional sample size?
Yeah. So usually what happens is, it's a very good question actually. When I was talking about the national oral health surveys, the national mental health surveys, we do multi-stage cluster random sampling. So what actually we mean by multi-stage cluster random sampling is the clusters which are larger in size, they have more probability of getting selected into the sample, and reasonably so. Let us say there is a village with 2000 people and there is another village with 200 people. What if the selection probability for participants in both these villages is same? If the selection probability for both these villages is same, you are recruiting more participants from a village, relatively more percentage of participants from a village, which is very small. So it cannot be so. What you want to do is you want to respect the fact that this is a bigger village. There are more number of people in that village and you recruit more people from that village. That is what we call as probability proportional to size. That automatically happens in cluster random sampling. But the way you adjust it is using your sampling weights. Once you have done everything, you use sampling weights to extrapolate it to a nation, to extrapolate it to a state, to extrapolate it to a district, depending on your primary, secondary, and tertiary sampling units.
Any other question?
There is one more from Dr. Anudars. Could you please explain about the sample size estimation for split mouth studies?
Yeah.
Or in vitro studies?
And in vitro studies, a very important question actually. So first we have to decide how we are analyzing the split mode data. No, I'll go back to, actually I'll take both these questions in an integrated way. So in vitro studies, what is happening is you are taking, let us say, a tooth specimen and then you are sectioning it. And in most studies, what they are doing is once you section the tooth into, let us say, four sections, once you section the tooth into four different sections, and you have 10 teeth, that makes 40 sections. That does not make your sample size to be 40. Your sample size is still 10 teeth because all the four sections that were sliced from the same tooth, they share a common characteristic of belonging to the tooth. And this is applicable even in the pit and fissure sealant retention studies and fluoride varnish studies. You cannot actually analyze the data at tooth level because those teeth, if you are doing a split mouth study, those teeth, they share a common trait of belonging to that same person who is having the same socioeconomic status, who is having the same sugar consumption frequency, who is having the same educational level, right? So these things, they have to be analyzed using paired tests. First, we have to understand that. And once you have shifted from an unpaired t-test to a paired t-test, the sample size logic remains the same. So whatever difference is there between two groups which are paired and unpaired, that applies in split mode studies as well. And then in vitro studies, usually what people think is that in vitro studies, you are essentially having all the specimens to be very similar. So what is the point in having so much sample size? There is no variation at all. Just because they are almost identical, almost similar, it does not mean that they are identical. Still, the temperature at which they are cured can be different. The microporosities can be different. The way the universal testing machine was used to test the fracture resistance can be different. So because of this, there is a need to calculate sample size even in vitro studies, but the sample size would definitely be less given the lesser amount of dispersion in vitro data.
There are more from Dr. Mithun.
Yes. Can you please read the question? Actually, I have
Yeah.
difficulty.
Sometimes while doing cross-sectional KAP studies, few says only chi-square test is enough and few say we need to check for the normality. and select the test. Can you please clarify, sir? Also, how does this affect the sample size?
See, when you said cap studies, the question is incomplete actually. So are you talking about a single population cap study where you are just assessing the knowledge, attitude, and practice in a given population, or are you trying to compare the knowledge between two different populations? So that decides what your statistical test is to be. Once you are just confining to a population, it is nothing but a descriptive statistic. You're just mentioning these many participants are having this knowledge, these many participants are having this attitude. But once you are trying to compare between these two, then you have to go for a chi-square test. And then coming to also how does this affect the sample size? Again, going back to which statistical test you use. If it is a single sample, if it is a single population about which you want to know, then you can go for a one sample proportion. When you are using the G star power, you will have a fixed amount of this is my baseline position, this is my null hypothesis where 40% will be the knowledge, but I wish to see an effect of 60%, so you calculate the sample size around that. But when you want to do a hypothesis test where you are comparing the knowledge between two different things, then you can, I'll actually show it here if I'm still sharing my screen. Yeah, just give me a moment to share my screen.
Yeah.
Yes. So now you can just go here, you can select chi-square test, and these are goodness of fit contingency tables. So you have an outcome variable which is dichotomous, and you have an independent variable which is also dichotomous. So that makes your degrees of freedom to be 1, which means, see, when you have a 2 into 2 contingency table, the degree of freedom is always 1. Because once in the 2 into 2 contingency table, one cell is filled, all the 3 automatically gets filled. Or if you go by the simple formula logic, it is row minus 1 into column minus 1. So the degree of freedom is 1. And then you have to determine your effect size because the number of cells is 4. Now you have to enter your H0 and H1 values, and the sample size estimation can be done. So that is another way of doing it if you are going for a hypothesis testing, not just estimation of cap in a given population.
I hope, Mithun, you got your answer. So one more is there. Sometimes in cluster random sampling, randomization is not done at the level of clusters. An intervention is done and outcome is assessed to the individual level.
Yes.
How
So
should you calculate the sample size at the level of cluster or participant?
Yes. So if you want to calculate your sample size at the level of the participants, you have to feed in the design effect. And coming to the analysis, so if your simple random sampling gives you a sample size of 400, I would actually take 800 participants. I'm not saying 800 clusters. So pay attention here, 800 participants. Because in the design effect itself, I have already fed the system how many units are there, how many participants are there in that cluster. So the first part of the question is answered. And then coming to if the design effect is not calculated, and if the design effect is not integrated into the sample size calculation, then you cannot assess or evaluate your data at a participant level. You have to use clusters as your primary unit of analysis. There, analyzing the data at a participant level is fundamentally wrong. Flawed.
Right. I hope, Dr. Dhanya, you got your answer. One last question is there, sir. Most of the in vitro microbiological studies, instead of calculating sample size, triplicates are taken. Should we calculate the sample size for those studies?
What is taken? Triplicates are taken. Yeah. Okay. So again, it is like, as I have already told you, the reason why it is done so is that people assume that there is very little variability. And when you are doing in triplicate, you are essentially doubting the testing that you are done. You are essentially saying that there can be variation in the testing which is being done, which is the very reason why you have to calculate sample size, which is the very reason why there will be a standard deviation associated and there will be an associated standard error, and still sample size calculation is a mandatory mechanism in vitro studies. And I'll just take this moment to also talk about how the probability theory has evolved. Do we have time for 2 minutes?
Yes, sir, sure.
Yeah.
Please continue.
So what happened is, see, when you are talking about all these things, the probability testing and all, this idea of probability actually started in 1600s, where they actually used it not for science, for gambling. Pascal and all, they used it for gambling. Then you must have heard about the Bayes theorem, the Bayesian statistics and all. In 1700s, somewhere around, I don't remember the exact year, but Thomas Bayes actually proposed something called as inverse probability. So we have to understand that before probability stepped in, it was actually inverse probability. See how beautiful the concept is. In probability theory, we are asking a question. If the null hypothesis is true, if I repeat the study, what is the probability of me seeing these things? Or even in simple intuitive terms, if there is no disease, what is the probability of observing these symptoms? That is what your probability theory is asking you. Whereas inverse probability theory, which is the Bayes theory, that is asking you, given these symptoms, what is the probability of having the disease? You understood the difference? And the later question, the Bayes question, is the general question what a common man asks. Given these symptoms, given these conditions, what is the probability of me having the disease? It is not the other way around, which is more intricate. So usually it is discussed like this. So you have an expectation that there is a probability of 40% rainfall tomorrow. So tomorrow there is a 40% chance to rain. And tomorrow when you wake up and went outside, you have seen hovering clouds in the sky. And then you decided to increase it to 60%. That is what Bayes' theorem is. You have a past belief, you have data, and then you will update your belief. That is what Bayes' theorem is. And whereas the probability theory is entirely data driven. So that is why I am referring to standard deviation and standard error in your question about using triplicates. So you are entirely dependent on your data. You are not depending on any past belief. So all your decisions are completely data driven. So the reason for this is that past belief does not make any sense back then, because we do not have complicated, sophisticated computers back then. But now we have all the Markov chains, Monte Carlo models, so which actually give some authenticity to past beliefs. So we can incorporate that with data, and then you will have an updated belief.
Yes. I hope this is clear now. There is one more query.
I think that should be the last one, Bakshi.
Last one.
Yeah,
Okay.
just take this one, then stop.
Okay, sure.
Move further.
So if the proportion is greater than the 50%, you have to take the smaller proportion in calculating the sample size for single proportion. So should we take
Can you repeat
relative
the question?
precision
It
or
says
absolute precision?
that if the proportion is greater than 50%, you have to take the smaller proportion. No, when the proportion is greater than 50%, what do we mean by taking a smaller proportion? I did not get the question actually. Could you please elaborate that question? So whoever who asked that question, because when you say the proportion is more than 50%, it is fixed. So what is the point of taking a smaller proportion? What is greater than 50%? So if you say greater than 50%, let's say 70%, the proportion is 70%. What do we mean by the smaller proportion? I did not get that.
Name is also not there.
Okay.
Okay. So one last, I think so we have. If we can take the oversample of a particular group to ensure there is enough data for analysis, what sampling method can be used?
Sorry, can you please repeat that question?
If we take oversample of a particular group to ensure there is enough data for analysis, what sampling method can be used?
No, if the question of enough data for analysis and the sampling method are completely different. No, enough data for analysis is a question of sample size. So we should not be clubbing it with the sampling technique. So those are two fundamentally different things. So, but the sampling technique does play a role when you are estimating your sample size. So that's what we have been talking about, the design effect and all. So when you feel that there is no real independence in the data that you are going to collect, you multiply your sample size calculated with and design effect. So that gives you a larger sample. So that would be enough sample size given that context, given that sampling technique. Otherwise, if you do not have any clustering, if you feel the data is independent, then whatever sample size you have calculated is good enough.
Yes, sir. I hope everyone
For
got
that
their
alpha
answer.
and power. For that alpha and power.
Yes, sir.
Thank you, Dr. Vishwa. I think you have very diligently tried to answer each and every question.
Thank you very much, sir. My pleasure.
Yeah. So my take, I don't know, my take is like, if you should consult a statistician initially when you are starting your research, when you have not calculated sample size before, I think it's better to go with the statistician, give him some values, and then you can learn from it. Maybe for in further studies you can try to you'll be able to calculate it, and how you have done. The study design is important. What you're trying to find out is important, and what type of study you're trying to do is very, very important. And than just the number. And yeah, the way you said the p value, I think we should we focus too much on p value. It just it doesn't make any sense. that we focus too much upon whether we got the significant difference or not. It's just the sample may not be the appropriate because we have not calculated. Most of us, we don't calculate the sample before we start the study. That's the basic defect what is there in most of the Indian research, I feel, or dentistry. So
Yes, sir.
with
And I'll just quickly
tell me.
would like to add one thing. So there is
Yeah, yeah,
something
sure.
called as a post hoc power analysis, which
Yeah.
researchers do. So once you find a non-significant result, we go back and say there might be an effect. We cannot rule out that there is no effect, but maybe my study is underpowered. So those sort of conclusions we should not be making. As you said, we should actually start our study by consulting a statistician. But there we are entering from a statistical territory to a practical territory where the responsibility lies on us to make the statistician understand what the study design is, what the biostatistical information we are talking about. So yeah, all this.
Okay, so I think we'll close it. Thank you so
Yes,
much.
sir.
And thanks. I'll thank all the participants who have stayed till now. Thank you so much, everyone. Have a nice evening. Good night. Yeah.
Thank you.
Thank you, everyone.
Thank you.
Bye.
We'll end the session, sir. Thank you so
Thank you.
much.
Thank you.
Thank you much.